Assalamualaikum warahmatullahi wabarakatuh and good morning everyone. Today we are pleasure to present our project titled Synthesis of Methane Simulation and Optimization using Aspen Plus. This project focus on Sabatier reaction, a catalyst process that converts carbon dioxide and hydrogen into methane, and the aims to improve the reaction parameters for enhanced efficiency and capability. Let me introduce my team. My name is Muhammad Hairul Zaman bin Muahidi with Esther Hong Jinye, Ezra Lika Anak James and Tan Hui Yu. Together, we are work collaborative to simulate and analyze the methane synthesis process using Aspen Plus. The synthesis of methane through the Sabatier reaction is an important process that involves the catalytic conversion of carbon dioxide and hydrogen into methane and water. This reaction plays a crucial role in carbon capture and utilization by reducing carbon dioxide emission and producing synthetic methane, which can serve as a renewable fuel. Despite its potential, the process has several challenges, being high exothermic, and it can lead to catalyst defection and incentive energy management. Furthermore, optimized parameters such as temperature, pressure, and feed composition is essential to achieve maximum methane yield and overall process efficiency. The aim of these studies is to analyze and optimize important parameters affecting methane generation, energy efficiency, and overall process performance by simulating the Sabatier reaction using an Aspen Plus. Our study has three main objectives. First, to use Aspen Plus to model the Sabatier reaction while taking kinetics and thermodynamics consideration. The second thing is to evaluate the effects of critical parameters such as temperature, pressure, and feed composition on methane yield and energy efficiency. And lastly is to propose recommendation for optimizing the reaction process based on the simulation result, addressing challenge in scalability and sustainability.
The literature review that we had conducted summarized about the Sabatier reaction, or also can be known as synthetic of methane. It's a reaction that converts carbon dioxide and hydrogens into methane and water. This reaction is a promising technology for renewable energy storage and carbon utilizations. The process is thermodynamically favorable at low temperature but kinetically limited, while high temperature improve reaction rates but reduce methane yield. Meanwhile, at high pressure and 4:1 hydrogen to CO2 ratio, it's optimized methane production. Last but not least, Aspen software helps in optimizing condition, although challenges like catalyst deactivation and heat management still remain. So this is the process flow diagram of the methodology study case. The process begins with a literature review to get the kinetic and thermodynamic data. The reaction is then modeled in Aspen and also involving all necessary parameters like reaction rates and equilibrium constants. Simulations are performed by varying key parameters such as temperature, pressure, and also feed compositions. Then, data on methane yield and energy efficiencies are analyzed to identify the trends. Optimizations involve sensitivity analysis to determine ideal operating conditions while evaluating scalability and also sustainability. Results are then validated through experimental data or literature comparisons to ensure its accuracy.
Now I would like to talk about our results. Based on this figure, methane and hydrogen being highly volatile, which are predominant in the vapor phase, whereas water dominates the liquid phase due to strong polarity and hydrogen bonding. Finally, is carbon dioxide exhibits moderate volatility, which distribute between both phases. Next, this is our graph. In this graph, we shows the relationship between the mole fraction of methane, temperature, and pressure. The mole fraction of methane increases with higher pressure, especially above 4 atm, and is highest near 10 atm. However, it decreases significantly as temperature rises above 350 Kelvin. Methane's mole fraction is more sensitive to pressure changes than temperature changes. Low temperature influence is likely greater at very low pressures. Rising temperatures will decrease the methane's vapor phase mole fraction due to increased evaporation of less volatile components, which alter the equilibrium. Methane have a high volatility, which ensures it dominates the vapor phase as pressure increases, consistent with Bragg's law and Dalton's law. Higher pressure enhances the methane's partial pressure, which more than less volatile components, significantly boosting its mole fraction in the vapor phase. And lastly, this is our another graph that shows the relationship between the mass flow rate of methane, temperature, and pressure. In this graph, there have a sharp decrease in flow rate as temperature decreases and pressure increases. Lower temperatures reduce the kinetic energy of methane molecules, which lead to condensation and a decrease in vapor phase flow rate. Higher pressure compress methane molecules, increasing the gas density and restricting molecular movement, and it will cause the gas to behave more like a liquid and reducing the mass flow rate. This behavior demonstrates methane's sensitivity to changes in temperature and pressure, where low temperature and high pressure significantly reduce the vapor phase flow rates.
Now, I would like to proceed with the conclusion. From this project, we can conclude that the Aspen software module accurately simulated the Sabatier reaction by considering both kinetic and thermodynamic considerations. Next, for the optimization, the simulation revealed that the higher reaction temperatures will improve the kinetic reaction, but reduce methane yield due to the thermodynamic limitations. Increasing the pressure will help to produce more methane, as this is because it shifted the reaction towards making more methane based on the reaction behaves. The amount and type of gases used in the feedstock had a big impact on the amount of methane was produced, highlighting the importance of optimizing the feed mixture for efficient methane generation. Next, for the suggestion, the process can be improved to identify better catalysts for the Sabatier reaction, as they should produce methane more quickly even at lower temperatures, and mainly produce methane to have lesser other unwanted substance. Next, for the recommendation, it is recommended to explore incorporating plasma into the reaction chamber. Plasma-assisted reaction allow operation at lower temperatures, reducing energy demands while maintaining high reaction rates. Next, it is advised to implement heat integration strategies to capture waste heat from the exothermic Sabatier reaction and utilize it to preheat the feedstock, reducing the overall energy consumption of the process. That's all from us. Thank you.